Okay, so here's a problem that asks us to compute the vertical deflection and rotation at C. So I'm going to start with just the deflection problem, and I'm also going to just do the bending part first. This is actually a fairly long problem to include both bending and axial for displacement and rotation. That's kind of like 4 problems in one. But we'll just do deflection and we'll do bending first, just to demonstrate. So looking at this problem, I know I'm going to have to generate moments for my real structure, and also imagine all the forces removed and just a virtual force of 1 at C. So that's very similar to this 10 kip force. So I'm going to go through each section and let's plot a little strategy. So if I want to cut the structure somewhere here, A to B, and my choice is to work the bottom half of the column or the top half of this L-shaped frame, you can go either way. The bottom half could be fairly simple, but you need reactions. The top half has a piece that looks identical and another component to deal with, but you don't need reactions. So I'm going to work that side of the cut. And we'll talk about the sign value when we get there, but I'm probably going to start it at the top and go down. And then the second piece would be to cut it somewhere between B and C. And I think the choices here are a little more clear-cut. We usually always like to use the cantilever end of the structure because there's less to deal with. So we'll work to the right side of that. So that's going to be my strategy. So let's first start with the real moments. And we'll start with the first section. Let's do the simplest one first. Let's do BC first. So my free body diagram would be this little piece to the right, which only has a 10 kip load on it. And I'm going to assume my unit X, or my coordinate X, goes from right to left. And then I'll have internally, all I'm looking for now is the moment. I was just thinking that it wouldn't be that much effort while we're here to go ahead and find what? The axial force, right? Because the axial force I would just assume is in tension and would be the force in BC. That wouldn't be, we could maybe get that information while we're going. So let's try that. So with that said, I would sum the moments at the cut that I've just defined, make sure it's in equilibrium. When I look at this free body diagram, my assumed direction for the moment is positive or negative with my sign convention. Negative, right? And then the 10 kip force on the end at a moment arm of X is also creating negative moment. So the moment is simply just minus 10x. Okay? And we can also sum forces in the X direction, make sure that's in equilibrium. You look at the X direction, I've got minus the force in BC, and what else? Nothing. So there is no axial force in that element. Okay with that? So now let's look at the next section, the section from A to B. Now from our previous discussion, we've already decided to work the top section. So let me sketch that out real quick. So over here on the far right, the cantilever section, I've got my 10 kips. That's 10 feet out. And then I've got this distributed load. and that has a value of 1/2 kips per foot. And I'm going to decide that that unit goes in this direction, some value y. I'm also going to assume internally that this is my moment and that this is my axial force. So this will be my force in AB. This will be my moment in AB. I guess I should have also called this BC. And let me just keep track of them that way. Sorry about that. So now I'll just come over in some moments at this cut that we've just formed in AB and make sure it's in equilibrium. So when we do that, the moment that I've assumed here is positive. And what else do we have? Well, I need to probably deal with this concentrated equivalent force. What would it be? Well, it's a rectangle. Base times height. Base is y. Height is 1/2. So this will be a force of y over 2, right? And what is the distance from the cut to the centroid? Half the distance, which is y over 2. About the cut, that's going to create negative moment. So I'm going to have minus the force y over 2 times the distance y over 2. That's an interesting coincidence, but that's just the way it is. And then also about the cut, I'm looking at the moment due to this 10 kip force, and that's going to be also negative moment. So that'll be minus 10 kips times a moment arm of 10 feet. So it looks like my moment in AB is going to be equal to, change all that over, it looks like I've got y squared over 4 minus 100. And I got a little sloppy with my units here, so that should be moment, so that's going to be kip feet. Same thing over here, this will have units of kip feet. Then I'm going to sum forces in the y direction.
Would it be plus 100?
Yes, it would. Thank you. So I'm going to sum forces in the y direction because I'm looking for this tension force. It's actually acting down. And what other forces do I have in the y direction? This is horizontal. This is vertical, and it's also down. So it looks like the force in AB is minus 10 kips. So a little compression. So I have moment and axial force in BC and moment and axial force in AB. Okay? So what does my virtual system look like? So my virtual frame is going to look like this. Still fixed here at A, except I'm just going to have a load of 1. And that's it. It's actually 20 feet tall. So the same sections that I chose for my real moment, the same directions I chose for the internal forces, I'll repeat here and find the virtual moment in those sections. So now I'll come back over and redo section BC, just like we did up here. So I will have, again, just the section to the right. The virtual load is 1. It's still a distance x from the right. I assume counterclockwise for my moment. I got to keep that, except this is the virtual moment from BC. And I assume tension here, so I'll do that again. And I'll use lowercase n. We've been using that before for our virtual force, so I'll keep that up. So if I sum moments about the cut, make sure I have equilibrium, what do I have? Well, the internal moment is positive or negative? Negative. The force or the moment produced by this virtual force is also negative. So now I can find my virtual moment. It's simply just minus x. Now how is this one different from this one? Just a factor of 10, right? So if I were to divide this one by 10, I would get minus x. So that seems to correspond with what we've been doing. All right, see if I can squeeze this in here. So here's AB, section AB. And there's the section. I have my virtual load of 1 at a distance x. There is no horizontal force. That's been wiped away. I still have the same moment direction, which is now the lowercase, and then also for my axial force, which I'm using n. And I did also assume that had a distance from the top to the bottom of y. So again, if I sum moments at the cut equal to 0, what do I have for the moment? Well, that's a positive moment. And what else do I have? Oh, just the virtual load, creating moment about the cut, creates negative moment times a distance of 10 feet. So my virtual moment in AB looks like it's just 10 feet. Everybody see that? Now that one you can't compare to this one because it's a different loading system. Did I do that right? Yeah. Okay, so we can finish by summing forces in the y direction, making sure it's in equilibrium. And what do I have? I have the virtual force in AB. I messed that up. That's acting down. And then minus 1. So my virtual force AB is minus 1. Sorry about that. So I have all the pieces I need now. I think what I'll do is I'll try to squeeze it in. I know it's going to be kind of messy, but I'll make a little box here to kind of border it off, and I'll see if I can put my displacement at C, what that equation is going to be. So I'm going to have 1 over EI, and what I'm going to have? Well, let's start with AB. So the section AB goes from 0 to, no, from the top, it goes from 0 down to the bottom, which is 20, 0 to 20. And the real moment is this thing, right? And the virtual moment is this thing. So I'll have a real moment of y squared over 4 plus 100 and a virtual moment of 10. And integrate that dy. And then I'm going to add to it the piece from C to B, which is an integral over that length, which is 0 to 10. The real moment there is minus 10x, and the virtual moment is minus x. and that would be integrated dx. Let me close it up. That would be too hard to do. In fact, this term's pretty easy to do. That's just 10x squared. You have to do just a little multiplication here, but not very much. I think I'll just stop there. That's good enough for me. Again, maybe on the next page, I'll go ahead and finish this, and when I post the PDF, I'll go ahead and do the calculation.
Is that y squared before or a squared?
Which one? Well, we wrote all of our stuff for a to b in terms of y. So we're integrating dy. And then all of our equations for BC were written in terms of x. And it's integrated dx. Now we could go ahead and do the axial component, right? We have all the axial forces. So that's the bending part. You would then add to it what? The real force times the virtual force times L divided by AE. Well, what's the in segment AB? The real force is minus 10, and the virtual force is minus 1. The length of that element, I'll write this way: the length of AB, and then of course you would divide that by AE. Now, what about the additional contribution from B to C? Well, the axial load in BC is 0. So that's it. So this now is the total displacement at C. This integral when evaluated would be the bending component, and this piece added up would be the axial component. You can see the signs cancel here, so it makes a positive contribution. This is positive. These negatives cancel, so positive. So all of these will create positive displacement or positive contributions to the displacement at C. So any questions about that? So I'll finish this up on the next page and post that in the PDF. And the one we haven't done is to rework the whole problem for rotation. Now, do we have to rework the whole problem? No, we've already got the real moments, right? I would just have to go back and redo my virtual system, which would generate those bits. So I think what I'll do is maybe at my desk later today, I'll work that problem and post that as a second part of this problem. So for homework, I'll try to give you some starter problems and not overwhelm you too much the first day out.